Hi everybody. 11.4, we're going to look at corresponding parts of similar triangles, so other possible segments in triangles that have this same relationship as well. So we need to do a quick vocab review of these objects first. We're going to look at an altitude, a median, and an angle bisector. Okay, I think the best thing would just be, let's sketch all three of these, quick little review of what they are. I'll talk through the definition as well. So if you remember, an altitude is used to measure the height of a triangle. There are three different altitudes we could draw, one from each vertex. It always goes from the vertex perpendicular to the opposite side. So typically we are used to, this is kind of the most straightforward example, from a vertex straight down to the opposite side. Remember, sometimes it does have to fall outside of the triangle. Median goes from a vertex to a midpoint. So pick a side, label that point as the midpoint, and then the median connects from there to the opposite vertex. And then an angle bisector, oh, and by the way, there's three of those as well, right? We could choose any vertex to start with there. And then an angle bisector does exactly what it says. Sorry, it's very hard to draw triangles on this little slate I'm using. Sorry about that. We take an angle, we cut it in half. We're talking about just the segment that falls within the triangle though. So that's an important piece of this. We want to be able to measure them to compare their lengths. Now, not surprisingly, and we're just going to jump right to the conjecture here, we would have spent some time on a little investigation, maybe even constructing them with our compass, but not surprisingly, these segments follow the same relationship as the sides in that they are also proportional. Okay, so if two triangles are similar, we'll use our new symbol here. If two triangles are similar, then the lengths of, and we're going to list all three here, so the lengths of the corresponding altitudes, medians, whoops, and angle bisectors are proportional to the lengths of the sides. Oh, my pen is frozen here. They're proportional to the lengths of the corresponding sides. Okay, so they have that same relationship as the sides do. We'll use the same ratio. So when you are solving problems with any of these new parts of the triangles, altitudes, medians, angle bisectors, it's just like all the other problems that we've done. We would just match up, angle bisector to angle bisector is, maybe 3 to 4, or altitude to altitude is 7 to 15, whatever the ratio might be. You solve those problems the same exact way. So there is one more piece we're going to add with an angle bisector. This is totally different setup. We're going to look at an angle bisector, just a single one in a single triangle, and see what it does to an opposite side. So for now, we're just going to sketch this. If we were in class, we would be constructing with our compass, taking some measurements with a ruler, but let's just sketch this for now, and I'm going to try to actually get a nice triangle out of my drawing here. Okay, so sketch a triangle with me. Oh boy. Try that again. Okay. And then I want to, for now, we'll just sketch the angle bisector. Okay, so I'm going to try to make it look like roughly, cut that angle in half. Does that look pretty good? Okay, so this is the angle that I'm bisecting here. And let's put some labels on here as well. So I'm going to call this triangle ABC, but A, sorry, put those on there out of order. A as the angle that we bisected, and then where it intersects the other side, call that point D. So there are a couple ratios we're going to look at here. If I look at the ratio of the two sides that make up that angle that we're focusing on, so let's say AB to AC, okay, so if I take this kind of longer side to this shorter side, it is actually the same as, and you could try to do this and take some measurements on your own, it's the same as BD to CD. So that longer piece over there to the shorter piece. So notice when we put the angle bisector in there, it breaks this side into two pieces, not two equal pieces, but they're more than just like, oh, two different lengths. They actually have the same ratio of these sides as well. So I'm going to write this out two different ways because you can actually, you know, we talked about there's technically 8 proportions you could set up for any one problem. So we could kind of rearrange this a little bit, but let me phrase it this way. So on this diagram, could you also label, we're going to call AB the long side, and then AC is the short side, so a full side of the triangle. And then BD is the long piece, CD is the short piece. So I'm going to write this a couple ways. The way we have it listed right now, if I take the ratio of the long side to the short side, that is equal to the ratio of the long piece to the short piece. Okay, so long side to short side is the same as long piece to short piece. I can also jumble that up a bit. Not just jumble it up, I mean we're being methodical here and correct how we write this out, but you could also compare this ratio. So look what I'm pointing at here, long side to long piece. So if I compare these two kind of longer parts there, longer length, so the long, oops, not longer, let's just say long side to long piece, that should have the same relationship as the short side to the short piece. But notice I'm being consistent with how I'm setting these up. So in this proportion, finish writing here. In this proportion, I have, you know, sides on the top, pieces on the bottom, long on the left, short on the right. It's all kind of nicely in its place. Over here, right, I've got sides on the left, pieces on the right, long on the top, short on the bottom. Let's do one of those bad ratios again. We haven't done that since earlier in the unit. So what I wouldn't want to do is compare like long side to short piece equals, you know, long piece to short side. There's no reason we would even want to take this ratio, the long side to the short piece. Okay, so just too much inconsistency there. Okay. Let me do 2 practice problems with you with this particular relationship. Oh, you know what? Let's write the conjecture down. Okay, it's kind of stated here in these proportions, but let's actually write this out in case you're having trouble following that. Okay, so let's say the bisector of an angle of a triangle divides the opposite side, this mark out of there, sorry. It divides the opposite side into 2 segments whose lengths are in the same ratio as the lengths of the 2 sides, this is a long one, as the lengths of the 2 sides forming the angle. Okay, so the way that we're reading this conjecture follows, let's see, this first proportion we set up. It's kind of phrased that way. So the bisector of an angle divides the opposite side into 2 segments, right? A longer piece and a shorter piece, whose lengths are in the same ratio. So the long piece to short piece ratio is the same as the lengths of the sides that make up that angle. That was angle A that we're referring to here. So that's long side to short side. Okay. If these proportions are helpful, I think these are maybe more helpful, but that's a we've got everything that we're very thorough. Okay, so now let's try practice problem number 2. Okay, so this one, you can see first check that you've got the angle bisector. Don't bother doing anything with it if it's not there. So what we want now, and I'm going to set up, maybe I'll do both of the proportions so you can see. So option 1, and let me maybe start with the shorter parts first. So if I do short side to short piece, 20 to V, that should equal long side to long piece, 45 over 36. We do the same thing as we have been. We cross multiply to get V all by itself eventually. It ends up being 16. So this was doing kind of short to short, long to long. Let me jumble that up a little bit. Let's totally change it around. So now I'm going to do long side to short side. Okay, so 45 over 20 equals long piece to short piece, 36 over V. You'll notice in either of these examples, let me kind of put the second step in here in either case. When you cross multiply, notice you're getting the same exact thing. I'm going to get 45V equals 20 times 36. What is that, 720? I should be able to do that in my head, but let me double check. My mental math is going away. Yeah, 720. Okay. Same thing over here. So when you cross multiply, there's 45V again. 36 times 20, there's your 720, divided by 45, we still get 16. So you can set it up either way, just whichever way your eyes kind of see it first. All right, so let's do a couple of practice problems together. If you haven't found this worksheet in the Google Classroom, pause this and go grab it. Either print it or keep it on the screen so we can look at these together. You can then finish them on your own, come back to the video. I'll show you my answers at the end of this video and talk through a few of them. There are a couple on here that are pretty challenging, so make sure you come back when you're done and check your answers. Okay, so we talked about the corresponding parts of similar triangles are also proportional. They also have that same ratio as the sides. So we're still starting out these problems, and I like to circle the pair of sides whose lengths I already have that are corresponding. Be careful with quite a few of these are kind of, the triangles are like flip-flopped. It's hard to tell which sides match up exactly. So that's where, again, these letters come into play here, right? ICE, AGE, the order of those is important. So from I to C to E, oops, excuse me, I to C to E, I know my alphabet. Then from A to G to E, so you can see it's kind of upside down and flipped around. Now this one's not that hard to tell just because of what's labeled here, but those are corresponding sides if I were to redraw the triangles. And remember, that's sometimes a good option. If you're really not sure which sides match up, just redraw them so they're facing the same way. Relabel everything. So I use this ratio, 22 to 33. You could use 33 to 22. You can reduce that if you'd like. You can just make it 2/3. That's fine. You don't have to. That's up to you, how you've been working through these. Okay, so if I have 22 over 33, I'm going to be doing 12 over H. So you might have set that up differently initially. That's okay. We're going to get the same answer at the end there. Okay, so we would cross multiply. We'd end up with the same thing. We end up getting H is 18. It does say everything's in centimeters here. Okay, so these, I guess I overlooked this. I should have mentioned this at the beginning. H is an altitude. We have the other corresponding altitude. We're going to set up a ratio using those sides as well. Okay, I'll let you try 2 on your own. Just be careful. Again, they're kind of flipped around. It's a little hard to see what's going on there. Number 3, triangle PIE. So the whole big thing is similar to SIC, just this little guy here. S is the midpoint of PI. Okay, so S is the midpoint of the big triangle. L is the midpoint of this little triangle. So let me mark this way. It's a little harder to mark, this full length because it's broken up into pieces. So what we're looking for is CL. So the whole point of the description of all this stuff being midpoints is just to tell you that you have medians. But medians are also proportional to the sides. So we can just use our side length ratio to set these up. Now these triangles are kind of facing the same way, so be careful here, our pair of sides for whose lengths we already have, that's 40 and 20. So maybe I want this ratio, 40 to 20 equals, now I'm going to do median to median. Bigger median on top, smaller median on the bottom. Okay, X ends up being 21 centimeters for that one. Okay, I think before you try them on your own, let me just comment the problems at the bottom. That's this new angle bisector conjecture. So short side over long side equals short piece over long piece, that one that we just went over. So make sure you're using that in 7, 8, and 9. Okay, so go ahead and finish these on your own. Pause this video and then come back to me and we'll go over the answers together. Okay, So let's take a look here. Numbers 1 and 3 we did. So there's number 2. I circled again the pair of sides whose lengths we already have. I used 18 and 24. So notice, as always, I've mentioned this throughout the unit, but you certainly could have a different proportion than me now that you've tried this on your own. That's perfectly fine. We're going to get the same answer at the end. Okay, so when we cross multiply, we're going to end up with the same result there. Okay, next group. Go ahead and take a look. Number 4, nothing too crazy. You're looking just for the length of this angle bisector here. Number 5. Oh, something interesting on this one. I don't know if, I'm assuming most of us solved it using 1.5 and 2.4, although we've never really talked about using half of a side. So what you may have found yourself doing, if you follow these tick marks here, this whole side is 3, this whole side is 4.8, but if you set that up, I'm going to actually just tack on an equal sign here. 3 to 4.8 is the same as 1.5 to 2.4, right? I just cut both of these numbers in half. So whether you use the full side or half the side, those are proportional, right? So it would be okay to use either ratio in that case. Okay. Something interesting to notice in number 6, and this is actually going to lead us to the next lesson. Even though the sides were doubled, I don't know if you caught that this bigger triangle is twice as big. Obviously not trying to scale super well, but that's the ratio that's there. The areas are not doubled, right? So 126 times 2 is not 504. I think that's just a kind of a little preview of what's to come. Okay, and then 7 is actually just like the example we did together, right? 20 over v equals 45 over 36. You absolutely could have had a different proportion initially. Just make sure you're not kind of jumbling things around. We would never want to put the short side with the long piece, right, in one fraction. There's no reason to compare those. Number 8 is fairly straightforward. There's one example of a proportion there for you. So I did short side over long side equals short piece over long piece. You can absolutely do like short side over short piece. So maybe you have 40 over 34. That's fine. Then you would just have y over 51. That's perfectly fine. Number 9 was a bit of a doozy. I don't know if you got this far on this one. So if you got 4.4, repeating, way to go. Super proud of you on that one. That one is really tricky. Because the tricky thing is here, so we've got this angle bisector, but we know the two pieces add to 10, but we do not know what each side is individually. They're not 5 and 5, right? Look at these. That doesn't necessarily cut that in half. The only time that would happen is if this was an isosceles triangle here, but it's not. So here's what we need to do. We can only have one variable in there. So if you think about this side, we're calling x, and we know together these two pieces make up a total of 10 units or centimeters. So this would have to be 10 minus x, this little squiggly piece right here. So now let me set up a proportion. I'm going to do the longer side over, that would have to be the longer piece. So 15 over 10 minus x equals shorter side over shorter piece, 12 over x. Now, we cross multiply the same way. Earlier in the unit, we did see some slightly more complicated proportions to work with algebraically, but we're still going to get diagonally here 15x equals 12 times this whole quantity, 10 minus x, so I do need to distribute that through. So let me do that, 120 minus 12x, and then I'm going to add 12x to both sides and divide by 27. So the exact answer, if you wanted to leave it like this, 120 over 27, but that's about 4.4, repeating, or 4 and 4/9, I think that is, centimeters. Okay, and then you could calculate the other one, right? It would just be, what, about 5.6, not quite 5.6, because those had to add to 10 together. Okay, that's all for today. Have a great day, everybody.